Hello guys, welcome back to my channel, and in this particular video we'll be tackling a truly monstrous, horrendous, evil integral. So let's get started now, and you'll see the real horror for yourself. Okay, so the real pain that we're going to be tackling in this video, let's call it I. It's defined as integral from 0 to infinity of natural log of x over 1 plus x squared times 1 plus x cubed dx. And noticing the form of the integrand we have here, if you're a true avid viewer of my channel, your inner gut feeling will tell you to use partial fraction decomposition, because the denominator is expressed as a product of two different factors. So say if we were to do that, we would obtain, and I'm not going to show all the steps, we'll obtain half of integral from 0 to infinity of x plus 1 times natural log of x divided by 1 plus x squared dx minus half of integral from 0 to infinity of x squared minus x plus x minus 1 times natural log of x over 1 plus x cubed dx. And if we do this partial fraction decomposition, splitting this second integral into chunks of x squared over 1 plus x cubed, and then x over 1 plus x cubed minus 1 over 1 plus x cubed, along with the natural log, splitting this up into three different integrals, the second integral, we get a weird value, but nonetheless we get a value. And you might believe that this technique is seeming to work, because we got a weird value, at least a value for the second integral. But then the problem lies in this first integral, because this, however hard you try to um, deal with it, you will always end up at an infinity. So it's always diverging. So divergent value, or infinity plus minus some constant, is still going to be divergent. So this results in a divergence, which is pretty much not the answer that we are looking for. So this method fails badly. So say we, on splitting this integral into two integrals, um, one of them gave a weird value, which is still okay, but other gave a divergent value, which means splitting them up like this is a bad idea, because one of them is diverging. So we need to recombine these integrals together and then do some sort of simplification on them. And one observation, or rather years of practice, have told me that if you have an integral from 0 to infinity of some function h of x dx, and trying other methods like the one we originally tried gives you a divergent value when it's not supposed to be divergent, actually is screaming that we make a clever substitution. So one substitution that works is u equals 1 over x. This works because it's some sort of symmetry substitution that we do, but it's specific for infinity, because if you have a fraction in the limit as x tend to infinity of 1 over x, that will go to 0, and then 1 over 0 will be infinity. So upper and lower bounds are getting reversed, and then we have a negative to correct that. So it's some sort of symmetry for zeros and infinity improper integrals. But if you try to do this method on this, it won't result in any good. I mean, it will make the question look even more complicated and ugly. So even this is not going to work. Now one trick that works is splitting this interval of 0 to infinity of as 0 to 1 h of x dx plus integral from 1 to infinity h of x dx, and then apply this infinity symmetry, if you want to call that, this reciprocal substitution on this second integral that we have. So let's go ahead and do this method, because I've solved this question before after struggling a lot with divergence issues, but trust me, this method works. So these are different techniques that you can use to tackle integrals that blow up to infinity when they should not. So one is, if they are split up, don't split them up, write them as one integrand. And the second thing you can do, you can try using the infinity symmetry or reciprocal substitution, like u is equal to 1 over x, hoping that this changes some stuff, and this works in some integrals. And even if this doesn't work, then you go ahead and split your interval like this, from 0 to 1 and then from 1 to infinity, and for the 1 to infinity integral, then you use the reciprocal substitution of u is equal to 1 over x. And if it's pretty unclear to you why this third method is going to help us, you'll see in a bit. I'm going to just do the exact same thing for I. So as discussed, I would like to split this interval from 0 to 1 of the argument, the integrands are as it is, plus integral from 1 to infinity of natural log of x divided by 1 plus x squared times 1 plus x cubed dx. And what did I say? For this second integral that we have from 1 to infinity, let's use the reciprocal substitution. So let x equal 1 over t, or t equal 1 over x, both are the same. Dx will naturally be negative 1 over t squared dt. So I just becomes the first integral as it is, 0 to 1 natural log of x over 1 plus x squared times 1 plus x cubed dx, plus for x equals 1, t will be 1, and for x tending to infinity, t will just be 0. And the natural log of x can be written as natural log of 1 over t over 1 plus 1 over t squared times 1 plus 1 over t cubed, and then this dx factor is the negative dt over t squared. Now first integral as it is, 1 plus x squared multiplied with 1 plus x cubed dx. This negative can be used to flip the upper and lower bounds, 0 to 1, but natural log of 1 over t can be written as negative natural log of t over, taking the LCM here, we have t squared plus 1 over t squared and t cubed plus 1 over t cubed and dt over t squared. So one thing you can notice is this t squared and t squared are cancelling out. So in the end, we just have integral from 0 to 1 of natural log of x over 1 plus x squared 1 plus x cubed dx minus integral from 0 to 1 of natural log of t, and this t cube will go on top, we'll have a t cubed, and all the rest is as it is, t squared plus 1 times t cube plus 1 dt. And it doesn't matter what variable we have as long as the upper and lower bounds of integration and the integrand itself remain the same. So we can actually change our t into our x directly. So I hope you don't mind the overwriting, but I'm going to do this to prove a point. So now what I'm going to do is I'm going to combine both of these integrals. So take a negative outside, factorize a negative basically. You have integral from 0 to 1 of x cubed times natural log of x. We converted everything to x. Minus natural log of x over 1 plus x squared times 1 plus x cubed dx. So factorizing out a bunch of things like this natural log of x multiplied with x cubed minus 1 over 1 plus x squared times 1 plus x cubed dx. So now one motivation we have is to basically get rid of this cubic denominator. The cubics are really annoying. Quadratics are still okay. Cubics, they just eat the flesh out of you. So I'm going to try to mimic the denominator on top. So we have minus integral from 0 to 1 of natural log of x and x cubed plus 1 divided by 1 plus x cubed times 1 plus x cubed dx. And since we obtained a positive 1, which means we added and subtracted 2 on both sides. So to obtain plus 1 we had to add 2, and therefore the other bit, the other integral is having a negative 2. That negative and this negative will be a positive 2 times integral from 0 to 1 of natural log of x over 1 plus x squared times 1 plus x cubed dx. Best part, these cancel out, so we just have call this part, I'm saying call this part I naught, and write this as it is. So we have minus integral from 0 to 1 of natural log of x over 1 plus x squared dx. Fair enough. And we have a 2 I naught like this. That's the general equation for I. And now what I'm going to do is I'm going to actually express I naught on a fresh page. See you there. So the I naught we obtained was basically this expression. And now I'm going to do quite an unsuspected thing, partial fraction decomposition on this. But you'll say, hey, wait, how is that going to work? Because last time we tried partial fraction decomposition, we got one integral, we got a value for that, but the second partial fraction decomposition part, we obtained infinity. But that's not going to be the case because of the sole reason that we've changed our upper and lower bounds of integration. So on 0 to 1, this integral is perfectly convergent. So using partial fraction decomposition, the basic, the same partial fraction decomposition that failed us at the start. So I naught can be expressed as half of integral from 0 to 1 of x plus 1 times natural log of x over 1 plus x squared dx minus half of integral from 0 to 1 of x squared plus x minus 1 times the natural log of x over 1 plus x cubed dx. So x squared and x cubed have basically been split up using partial fraction decomposition. And now pull out the halves from both the integrals. We have 2 I naught is equal to, split these up into different integrals. So integral from 0 to 1 of x times the natural log of x over 1 plus x squared dx plus integral from 0 to 1 of natural log of x over 1 plus x squared dx, and we're having negative integral from 0 to 1 of x squared times natural log of x over 1 plus x cubed dx minus integral from 0 to 1 of x times natural log of x over 1 plus x cubed dx plus integral from 0 to 1 of natural log of x over 1 plus x cubed dx. And at this point you may be crying because this monster integral just wants to torture us more. It just spat out more integrals for us to calculate. But let's just go get on with it. So call this I1, call this along with the negative to be I2, and then this along with the negative, call this to be I3, and this along with no negative, so don't bother, I4. So let's calculate each of them separately and then plug them back into the 2I0 equation. So I1 now is equal to integral from 0 to 1 of x times the natural log of x over 1 plus x squared dx. So in order to match the derivative of the denominator on top in the numerator, I multiply and divide by 2. So I have 2x times natural log of x over 1 plus x squared dx. And why did I do that? Because now I can use integration by parts. This 2x over 1 plus x squared will be the function I anti-differentiate or integrate indefinitely. This natural log of x, being a natural log, will have to be differentiated. So when I apply integration by parts on this, I have half times antiderivative of 2x over 1 plus x squared is just natural log of 1 plus x squared. And then this term as it is, natural log of x evaluated from 0 to 1 minus half of integral from 0 to 1 of natural log of 1 plus x squared over x dx. Now at 1 we have natural log of 1 times natural log of 2. Natural log of 1 will make the entire thing go to 0. But at natural log of 0, if you plug that in, you have natural log of 1 times natural log of 0. Natural log of 0 is negative infinity. Natural log of 1 is 0. So we have a 0 times infinity situation. Looks like it can be dealt with more carefully. So we basically have a 0 times infinity situation. So we can write this limit as x goes to 0 of natural log of 1 plus x squared divided by, I can write this as natural log of x to the negative 1 power. And now notice we have a 0 over 0 situation, so we can totally apply L'Hopital's rule. That's the short form for L'Hopital's rule. We will obtain limit as x goes to infinity of 2x over 1 plus x squared divided by negative natural log of x to the negative 2 power times 1 over x. So this will just give us limit as x goes to infinity of 2x squared over 1 plus x squared all divided by negative natural log of x to the negative 2 power. And the numerator, if you plug in x equals 0, is again 0 over 0 situation. So what can we do exactly? The thing is, if you keep on applying L'Hopital's rule again and again, eventually this quadratic on top will just get reduced down to a linear. So, if I just 1 plus x square, if I ignore that it's a multiplicative factor, we can write it as a separate limit and then evaluate that to 1, plugging in 0. We just have 2x squared over this factor, which can be, again, applied L'Hopital rule on. So we have 4x divided by 2 times natural log of x to the negative third power, and a 1 over x will get an x squared on top. So this process will go on, but the thing is the natural log grows way slower than a polynomial term. So in all, this will go to 0. You can cleverly do keep on applying L'Hopital's rule. I'm not going to do that again. So for both cases it goes to 0. So entirely this term will go to 0. So we just have minus half times integral from 0 to 1 of natural log of 1 plus x squared over x dx. And noticing the denominator and the structure of the natural log, we can use the Taylor series and bring the sum outside, interchange the sum and the integral, assuming uniform convergence. So we have minus half times sum from k equals 1 to infinity of minus 1 to the k plus 1 over k times integral from 0 to 1. We have x to the 2k, and then this x will give us x to the 2k minus 1 dx. And we have minus half times sum from k equals 1 to infinity of minus 1 to the k plus 1 over 2k squared times x to the 2k evaluated from 0 to 1. This will entirely be 1, so don't need to bother about that. We have negative half, negative 1/4 actually, times sum from k equals 1 to infinity of minus 1 to the k plus 1 over k squared. This is just the Dirichlet of 2, which has a value of pi squared over 12. So entirely I1 is just negative pi squared over 48. Fascinating, but that's the value of this integral. Moving our integral expressed to I2, we are taking the negative, so we have negative times integral from 0 to 1 of x squared times natural log of x over 1 plus x cubed dx. So noticing a quadratic on top and a cubic in the denominator, we can again use the trick that we applied last time, except we're multiplying and dividing by a factor of 3 to match with the derivative of the denominator, 3x squared divided by 1 plus x cubed dx. And I did this because we're going to apply integration by parts. So we will be integrating this while we patiently differentiate this. So we have negative 1 over 3 times natural log of, antiderivative of this is 1 plus x cubed. I actually need an absolute value, but I won't bother because x is always positive, times natural log of x evaluated from 0 to 1 minus plus half of one third rather of integral from 0 to 1 of natural log of 1 plus x cubed divided by derivative of this is just 1 over x dx. So now for 1 we have natural log of 1 times natural log of 2, so that will become 0. And for natural log of 0 we'll have natural log of 1, which is 0, times natural log of 0, which is basically negative infinity. So 0 times infinity. We can apply L'Hopital's rule on this. Again, I won't be showing that. It's basically the same idea as before. After basically applying L'Hopital's rule once, you'll have a cubic or maybe even a biquadratic over a natural log to the negative power. And a polynomial always grows faster than a natural log. So the numerator will dominate and make the entire fraction go to 0. So this will go to 0, and we just have 1/3 times, I'm using Taylor series as before, and interchanging the sum and integral, sum from k equals 1 to infinity of minus 1 to the k plus 1 over k times integral from 0 to 1. We have x to the 3k divided by x, so x to the 3k minus 1 by laws of indices. This will just be 1/3 times sum from k equals 1 to infinity of minus 1 to the k plus 1 over 3k squared times x to the 3k evaluated from 0 to 1. This will go to 1. So we just have 1 over 9 times sum from k equals 1 to infinity of minus 1 to the k plus 1 over k squared. This again is the Dirichlet of 2, which has a value of pi squared over 12. So entirely this I2 will just be 1 over 9 times pi squared over 12, which is nothing but pi squared over 108 if you know your tables properly. And I3 now, so I3 is taking the negative in integral from 0 to 1 of x times natural log of x over 1 plus x cubed dx. But notice the answer we have here is going to be different, because now we're not going to employ the technique that we used for last time, basically integration by parts. We'll be using something else. So notice that the interval is from 0 to 1, and we have something of the form a over 1 minus r. Here r is negative, x cubed. There's an indication that we can use geometric series, because again our common ratio r is within the radius of convergence, which is between 0 to 1. So let's just rewrite this properly, so you can see what I'm talking about. So we can write this as 1 minus negative x cubed dx. So comparing this denominator to this form we had, a is just 1 and r is just negative x cubed, but this is the formula for the infinite geometric series. If absolute value of r was less than 1, absolute value of this thing x cubed is less than 1, because x is from 0 to 1, so x is like some weird fraction, and x cubed is even smaller. So this inequality is therefore satisfied, because if x is absolute value of x is less than 1, then x cubed being even smaller will also be less than 1. So that's therefore we can, since we are in a radius of convergence, we can write this as a geometric series. So from this, S was basically sum from k equals 1 to infinity of a times r to the k minus 1. So a is 1, so don't need to bother about that. We have take the minus outside. Again, we can interchange the sum and the integral. Sum from k equals 1 to infinity of, we'll have minus x cubed to the k minus 1 power, or basically minus 1 to the k minus 1 power times integral from 0 to 1, and x to the x cubed basically to the k minus 1 power times this x times this natural log of x dx. So we can split this up into minus 1 to the k times minus 1 to the negative 1, minus 1 to the negative 1, and this negative will cancel out. So we just have sum from k equals 1 to infinity of minus 1 to the k, and then integral from 0 to 1 of, this is x to the 3k minus 3 plus 1 because of this x, so x to the 3k minus 2 times natural log of x dx. And at this point we can totally apply integration by parts. We can integrate this while we differentiate this. So we just obtain sum from k equals 1 to infinity of minus 1 to the k divided by 3k minus 1 polynomial antiderivative, and we have x to the 3k minus 1 times natural log of x evaluated from 0 to 1 minus integral from 0 to 1 of x to the 3k minus 1 divided by x because of the derivative of this natural log. So x to the 3k minus 2 power dx. So this natural log of 1 is 0, goes to 0, and for the 0 case you have 0 times infinity again. You can apply L'Hopital's rule. It's basically again now this time it's a clear polynomial. No need to even take a L'Hopital's rule once. It's going to go to 0, making this entire thing go to 0. So we just have sum from k equals 1 to infinity of minus 1 to the k over, and antiderivative of this we'll have a negative because of this 3k minus 1 times 3k minus 1, so 3k minus 1 squared times x to the 3k minus 1 evaluated from 0 to 1. This will go to 1, and we can write this is minus sum from k equals 1 to infinity minus 1 to the k over 3k minus 1 squared. Now you could write this in terms of Hurwitz zeta functions or something, or even Lerch transcendents, but I'm not going to do that. So our I3 is basically an unresolved series. Let's just keep it that way. Hopefully it'll just mellow down to a finite value with some other series, or I don't know, I'm just guessing. Let's see. Okay, so I4 now, integral from 0 to 1 of natural log of x over 1 plus x cubed dx. But the good news here is we are going to actually apply the same technique that we used for the last integral, basically using geometric series. So we can write this natural log of x divided by 1 minus negative x cubed dx. So again we are in our radius of convergence. We can again write this as a geometric series and then interchange the sum and the integral. So we have sum going from k equals 1 to infinity of the integral from 0 to 1 of minus x to the third power raised to the k minus 1th power times natural log of x dx. We can certainly pull out the negative 1 to the k. So we'll have negative 1 to the k minus 1. So we can split that up into negative 1 to the k and a negative sign, and integral from 0 to 1 of x to the 3k minus 3 times natural log of x dx. So now again integration by parts. Integrate this while we differentiate this minus sum from k equals 1 to infinity of minus 1 to the k over 3k minus 2, then x to the 3k minus 2 times natural log of x evaluated from 0 to 1 minus integral from 0 to 1 of x to the 3k minus 2 divided by x because of the derivative of this. So x to the 3k minus 3 power dx. Fair enough. Because of 1, natural log of 1, this goes to 0, and for 0 you can use L'Hopital's rule, entirely making this go to 0. This negative, that negative will cancel. We have sum from k equals 1 to infinity of minus 1 to the k divided by, we have 3k minus 2 times 3k minus 2. So 3k minus 2 entire thing squared, and we have x to the 3k minus 2 evaluated from 0 to 1. This, if you plug stuff in, goes to 1. Don't need to bother about that. So I4 is just another unresolved series from k equals 1 to infinity of minus 1 to the k over 3k minus 2 entire thing squared. Unresolved series again for I4. So now we have two unresolved series. Why don't we club them together? So Why don't we do I3 plus I4 and let's call that S. Let's do that on a fresh page. See you there. Okay, so as I said, here's the part where we're considering the unresolved series. So we add I3 and I4. So we have negative sum from k equals 1 to infinity of minus 1 to the k over 3k minus 1 entire thing squared minus sum from k equals 1 to infinity of minus 1 to the k over 3k minus 2 squared. And so if you want some perspective, we can write some terms of this series. So when we write stuff down, we have minus 1 over 2 squared plus 1 over 5 squared minus 1 over 8 squared going till infinity for this first series. And then for the second series, we'll have 1 over 1 squared minus 1 over 4 squared plus 1 over 7 squared, and that goes on till infinity for the second series. So if you just write these terms properly, clubbing terms from both series and writing them in sequence, we've 1 over 1 squared minus 1 over 2 squared minus 1 over 4 squared plus 1 over 5 squared plus 1 over 7 squared minus 1 over 8 squared, and so on. Notice that this is almost the Dirichlet eta function. The Dirichlet eta function of 2 was basically 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared, and so on basically. But although we are having the alternating part, but notice we are not having any multiples of 3. We skipped the 3, we skipped the 6 between 5 and 7, and we are again going to skip the 9. So we can write this is the Dirichlet eta of 2. So sum from k equals 1 to infinity of minus 1 to the k plus 1 over k squared minus all those alternating multiples of 3 squares that we had. So 3k, the whole thing squared, because 3k will always be a multiple of 3 because k is an integer. 3 times k, 3 times any integer is always going to be a multiple of 3. So that it will generate all these missing multiples of 3. So this series can be written as the original series with all the multiples of 3 minus the series that only has the multiples of 3. So in one way we are basically removing all the multiples of 3. And this will become, we know this value, Dirichlet eta of 2 is pi squared over 12. This is 1 over 3 squared or 1 over 9 times Dirichlet eta of 2, which is pi squared over 12. This will become pi squared over 108 minus pi squared over 12. So that's basically all our unresolved series. That's what they evaluate to finally. So now let's plug everything back into our original equation. So let's plug everything back into our 2I0 equation. So I1 turned out to be negative pi squared over 48, and then this second integral is as it is, and the reason I'm not evaluating this will be evident to you in a few minutes. And then this I2 turned out to just be pi squared over 108, and then these I3 and I4 basically turned out to be pi squared over 108 minus pi squared over 12. So that is actually significantly reducing the complexity of our question, because now all we are left with is this negative pi squared over 48 minus pi squared over 12 plus pi squared over 54 which roughly evaluates to negative 37 pi squared over 432. That's 2 times I naught, but we still have to add this unevaluated integral. So let's go ahead and plug everything back in our original I equation. So now plugging everything back, I is 2 I naught we know is negative 37 pi squared over 432 plus integral from 0 to 1 of natural log of x over 1 plus x squared dx, and then this original minus integral from 0 to 1 of natural log of x over 1 plus x squared. So two integrals evaluated on the same upper and lower bounds having the same integrands subtracted from each other will cancel out to 0. So I is just negative 37 pi squared over 432. Isn't that a really nice answer? Given all the trouble we went through, it's really nice to write it this way. So now finally, just to put everything into a grand perspective, we had I originally defined as integral from 0 to infinity of natural log of x over 1 plus x squared times 1 plus x cubed dx. And since this, if we perform partial fraction decomposition on the original uh, upper and lower bounds, this was diverging. So we used one of the three observations of when we obtain divergent integrals when we should not. So the first technique we could do was, if they are two separate integrals, combine them together. So that told us partial fraction decomposition was out of the question. And the second point was, you could try reciprocal substitution, but directly doing that doesn't help us much. And the third method was split them as integral from 0 to 1 plus integral from 1 to infinity, and the second integral from 1 to infinity you use reciprocal substitution. And that tends to simplify as we obtained. And then we use partial fraction decomposition, got a bunch of integrals, which was a painstaking job to calculate, but uh, we finally got this nice answer of minus 37 pi squared over 432. Unexpected, the pi's drop in again out of nowhere with just a natural log and a polynomial factors in the denominator. But that's how life is, that's how math is. That's it for this video. I hope you enjoyed this truly monstrous integral. So yeah, please like, share and subscribe to my channel, guys. I want more subscribers, more views, more likes per video. In the meantime, stay home, stay safe, have a great day, keep on doing math, and don't forget to peace out.